Okay, we're going to continue our discussion of energy, but talking about the discussion of thermal energy. And thermal energy is a special type, if you will, of kinetic energy. Thermal energy is the internal energy of an object due to the random motion of its molecules. And the temperature of any object is the average kinetic energy of all the molecules that are in the mass. Now, for example, if you have two bodies, the one on the left and one on the right, you see that each one has molecules that are moving around inside. And the thermal energy of any particular body is the total kinetic energy of the molecules that are within those two bodies. And because those two bodies are the same size, you would project that they would have that the one on the right would have a greater kinetic energy total and a greater thermal energy. The temperature, on the other hand, is related to the average, and so it takes into account differences in size. Remember, the average will take all the molecules and the total energy and divide that by the total number of molecules. And so in this case, because the total number of molecules are the same, the thermal energy is less on the left than on the right, and the temperature is also less on the left than on the right. However, there are situations where the temperature can be greater in an object, but it have less thermal energy if it's considerably smaller and has less mass than another object, which may have a lower temperature, but because of its greater mass, it would have greater total thermal energy. Now, what are some factors that affect thermal energy? Well, the temperature, obviously. The greater the temperature, the greater the thermal energy if the mass is the same. The state, that is, the degree in which, whether it's a solid, a liquid, or a gas, you can see that a gas, because of the liberation, would have greater kinetic energy given the same number of molecules. And so a gas would have greater kinetic energy and thus greater thermal energy than the same substance with the same number of molecules in a liquid state, which would have greater kinetic energy and greater thermal energy than a solid with the same number of molecules in the same situation. And then lastly, the mass. The greater the mass, the greater the thermal energy. And so you can overcome differences in temperature if the mass is different. And if one object has a much greater mass but a lower temperature, it can still have more thermal energy than something that is small but it has a higher temperature. For example, a pot of boiling water may have less thermal energy than a lake that's at 0 degrees centigrade, because the lake is a huge mass compared to a pot of boiling water. Now, there are various ways in which thermal energy can be transferred. And what tends to happen is when two objects come into contact, they reach what's called thermal equilibrium. And a state of thermal equilibrium occurs when no thermal energy is being transferred between objects that come together. Heat is transferred from one object to another, and it represents the transfer of thermal energy, and it occurs from a hot object to a cold object. So in this diagram, the thermal energy would transfer from the 100 degree to the 0 degree, and the heat would transfer from the 100 degree object to the 0 degree object. Now, the caloric theory was a historical theory that said that heat was a fluid that flowed from one body to another. But we now know that that is not the case. Now, heat capacity is defined as the relationship between the transfer of heat and the temperature, the amount of heat needed to change the temperature. So the thermal capacity is the amount of heat necessary to change the temperature. So on the left, you have an object that has a low or small heat capacity. So it does not take very much heat to raise its temperature. And so its heat capacity is represented by a smaller box. So the same amount of heat put in a larger box raises the temperature less. And so it has a much larger heat capacity. So the greater the heat capacity, the more heat that's required to raise the temperature. Specific heat is the heat capacity that's corrected or balanced for the size of the material. And so the specific heat is the heat capacity divided by the mass. And it is either in calories per gram degree centigrade or joules per gram degree centigrade. So heat of any object, or the heat capacity of any object, is the mass of that object times its specific heat times the change in temperature of that object. So the amount of temperature change that occurs with any given amount of heat will be represented by the amount Q. So let's take a look at these calculations, heat calculations. So 324 grams of an unknown substance at 45.8 degrees centigrade is dropped into 325.8 grams of water at 23.7 degrees centigrade. If the final temperature is 26.5 degrees, what is the heat capacity of this unknown substance? Well, let's take a look at how we would go about doing this. One thing you need to know that I haven't mentioned yet is that the heat that is lost by any hot object is equal to the heat that is gained by any cold object, as long as there is no transfer to the environment and as long as no work is performed. And so what we have here is the transfer of heat from this unknown object to water. And I will tell you that the specific heat of water, the CSP of water, is 1 calorie per gram per degree centigrade. So we can say that, the other way to say this is to put it as a conservation. The heat lost minus the heat gained, or is equal to 0. So that there has to be a conservation of energy. All the heat that's lost by one object has to be gained by the other object. So let's put, using our formula, which was back here, the mass times the specific heat times the change in temperature is equal to the mass times the specific heat of this object times its change in temperature. So the mass here, the unknown substance, is 324.4 times its specific heat, which we don't know, times its change in temperature. Now its change in temperature goes from 45.8 to 26.5. So 45.8 minus 26.5. And that has to equal the mass of water, which is 325.8, times its specific heat, which I told you is 1, and the change in temperature, which is going to be 23, or 26.5 minus 23.7. 26.5 minus 23.7. Now if we rearrange this, CSP is going to equal 325.8 times, and we subtract this, that's going to be 2.8 divided by 324.4, and the subtraction here is going to be 19.3. Now, just because I don't have a calculator, I'm going to assume that these two numbers are about the same. They're not, and so that means that this is going to be approximately equal to 2.8 divided by 19.3, which, if we say that's 3 and this is 18, that's 1 over 6, or about 0.1, let's say 5, something like that. So if you do get your calculator out and do the actual calculation, and you should get something close to 0.15 calories per gram degree centigrade. Now let's take a look at this second problem. A piece of copper that has this weight and has this specific heat is heated to 91.1 and is dropped into water at this temperature. What is the final temperature? Now this is a little more challenging. So we'll let TF equals the final temperature. And it's the same situation. The heat lost by the copper is going to equal the heat gained by the water. So the heat lost by the copper is going to be the mass of the copper times the specific heat of the copper times the change in temperature of the copper, and that's going to equal the mass of the water times the specific heat of water times the change in temperature of the water. The mass of the copper is 462 or 65.2. The specific heat of copper I gave you is 0.0911. And the change in temperature is going to be 91.1 minus TF, because TF is going to be lower than that. And I'm just doing it this way to make the signs easier. Now, that's going to have to equal the mass of water, 325.4. Must have been the same jug of water up here, or close to it. And it's going to be times 1, which is the specific heat of water, and the change in temperature here. And the final temperature is going to be higher in this case. So we're going to say TF minus 21.1. And now if we do the math here, we've got 325 times this, so 325.4 TF minus, and whatever 21.1 times this is, 325.4 times 21.1 is going to equal this multiplication minus this times, well, let me just write it out, 465.2 times 0.0911 times 91.1 minus 465.2 times 0.0911 TF. And you can move this over to this side and this over to this side and solve for TF. And again, I'm going to let you do that because I don't have a calculator. Now, there are ways in which we can do these various experiments, and these are two devices called calorimeters. And a calorimeter is a device that's designed to measure heat in a physical or chemical process. And the one on the left is the cheapo one, in which you use 2 styrofoam cups to insulate. The one on the right is the one you'll pay a lot of money for, in which case you have an automated stirrer, etc. And you can use these to do experiments with heat. Now the units of thermal energy are either going to be joules or calories, and you just have to make sure that you don't mix joules and calories. And 1 calorie is equal to 4.19 joules.